3.8 billion years ago, the universe began. In one moment, there was nothing, and in the next, everything. How this is possible remains one of the biggest questions in science, bridging theory and experiment, physics and philosophy. Our understanding of the universe relies on mechanisms, processes, and causality. We seek to understand why things are the way they are, yet at the most fundamental level, we still don't know how or why the universe came to be. This mystery persists despite centuries of exploration. Perhaps, as cosmologist Stephen Hawking once suggested, there truly was nothing before. If space and time are inseparable properties of the universe, then the beginning of the universe marked the beginning of time itself. Before time, there could be no space, and thus no universe. Hawking envisioned the geometry of space-time contracting and curving back through the ages, eventually rounding off. Searching for something beyond this would be as futile as seeking a point north of the North Pole. Alternatively, there may have been no true beginning, but rather a limit to our ability to observe. Scientists believe that a split-second period of exponential expansion, known as inflation, gave the Big Bang its bang and set the stage for everything that followed. While inflation in our universe lasted only a fraction of a second, some physicists argue that inflation continues eternally elsewhere, creating bubble universes within an infinite multiverse. Another theory, the Big Bounce, suggests our universe is part of an endless cycle of expansion and contraction, or perhaps our understanding of scale is incomplete. Physicist Roger Penrose proposed that the universe loses its sense of time and scale at the infinitely small and large, becoming equivalent in essence. Chess, for example, plays the same whether on a pocket-sized board or one spanning a courtyard. Another idea is that our universe emerged from a collision of dimensions. String theory posits that reality is composed of tiny vibrating strings within an 11-dimensional hyperspace. The three spatial dimensions and one time dimension we experience may be just one brain among many, with our universe's birth resulting from collisions between higher dimensional brains. Or perhaps the answer lies in some unexplored corner of mathematics or physics, still beyond our grasp. For now, the origin of the universe remains a mystery, a cosmic choose-your-own-adventure. Yet, 13.8 billion years ago, the universe did begin, and this is the story of what happened next. This is Proxima Centauri. Even traveling at over 50,000 kilometers per hour, it would take more than 80,000 years to reach Itor's closest star. The Milky Way alone contains an estimated 100 billion more distant stars. The vastness of the cosmos can feel overwhelming, making it challenging to reconcile our lives with the enormity of the universe. Sometimes it helps to have guidance. Space Shock is here to explore these profound questions, offering insights into the mysteries of the cosmos. Where is the hottest place in the universe? You might think it's the core of a star, where nuclear fusion occurs. Yet, even as you plunge through its fiery depths, temperatures reach only 15 million degrees Celsius. More violent cosmic events, like supernovae, eject superheated gas at 100 billion degrees Celsius. But even this isn't the hottest temperature recorded. That distinction belongs to CERN's Large Hadron Collider, where collisions between lead atoms briefly produce temperatures of 5.5 trillion degrees Celsius, 50 times hotter than a supernova. Still, this pales in comparison to the Planck temperature, the theoretical maximum of 1. 4 times 10 circumflex 32 Kelvin, where particles would disintegrate under their own energy. Max Planck, the father of quantum physics, introduced this concept along with the Planck lengths. 1. 6 times 10 circumflex negative 35 meters. And Planck time, 5.3, 9 times 10 circumflex negative 44 seconds. These units become crucial when considering the universe's earliest moments, when everything was compressed into a space smaller than a proton and temperatures reached Planck levels. This era, known as the Planck epoch, remains shrouded in mystery, as our current theories of gravity and quantum mechanics break down under such extreme conditions. The universe's expansion has made it less dense over time, but its origins are still debated. Some theories suggest it began infinitely large, while others propose it started as a single point. The observable universe, limited by the speed of light, is just a fraction of the whole. As we look back in time, the observable universe shrinks, eventually reaching the Planck epoch, where all forces were unified. During this time, gravity, the first force to manifest, dominated. However, our understanding of gravity, based on Einstein's general relativity, fails at quantum scales. This has led physicists to seek a theory of quantum gravity, which could reconcile relativity with quantum mechanics. Candidates include string theory, loop quantum gravity, and the hypothetical graviton. Each theory is more abstract than the last, rooted in complex mathematics and nearly impossible to visualize. Yet, these ideas help us imagine the universe's earliest moments, a turbulent quantum foam where space-time itself was unpredictable. After the Planck epoch, the universe enters the grand unification era, where 3 of the 4 fundamental forces, electromagnetism, the weak force, and the strong force, were unified. At these extreme energies, particles underwent constant transformations, creating a chaotic soup of matter and antimatter. This era ended when temperatures dropped enough for the strong force to separate, leaving 3 distinct forces. Yet, these theories struggle to explain the large-scale structure of the universe we see today. Observations from the James Webb Space Telescope have revealed galaxies forming much earlier than expected, challenging existing models of cosmic evolution. While these findings don't disprove the Big Bang, they highlight gaps in our understanding. The universe's large-scale structure also presents puzzles, such as the horizon problem, why the universe is so uniform, and the flatness problem, why space-time appears flat. These issues led physicist Alan Guth to propose cosmic inflation, a period of exponential expansion that occurred less than a trillionth of a second after the Big Bang. Inflation explains how the universe could have grown from a tiny, hot, dense state to the vast, cold cosmos we see today. It also accounts for the absence of magnetic monopoles, another mystery of the early universe. While inflation remains a compelling solution, it underscores how much we still have to learn about the universe's origins and evolution. But if we are only observing a tiny fraction of the universe, it's impossible to determine its overall curvature. It might simply be a matter of perspective. From the shore, The ocean's horizon appears flat, but only from a higher vantage point do we see its true curvature. Similarly, the wider cosmos could be positively curved, negatively curved, or a complex combination of both, but our limited view prevents us from seeing beyond our cosmic shore. As for the absence of magnetic monopoles, this is only puzzling if we assume they are missing from the entire universe. If they existed in the early universe, in the quantities predicted by current models, exponential inflation would have spread them so thinly that we might expect to find only one monopole per observable universe. Searching for a single monopole within a sphere 93 billion light-years across is no small task, which explains why we haven't found one yet. Inflation is now a cornerstone of our understanding of the universe's earliest moments. Since Alan Gough's groundbreaking proposal 40 years ago, cosmologists have worked to uncover the mechanism behind this rapid expansion. The timing of inflation coincides with the energy drop that ended the grand unification of fundamental forces and allowed the strong nuclear force to emerge. Some scientists theorize that the decay of X bosons, which carried the electro-strong force, created an inflation field mediated by a new particle called the inflaton. This inflaton-driven energy caused the universe to expand exponentially, magnifying quantum-scale irregularities into the large-scale structures we see today. These fluctuations became the seeds for galactic clusters and superclusters. As the universe expanded, it cooled and emptied, leading to a 100,000-fold drop in energy. The exact reason inflation stopped remains unclear, but when it did, the inflaton field decayed, releasing energy back into the universe in a process called reheating. This energy allowed for the creation of matter, setting the stage for the next phase of cosmic evolution. By the time the universe reached the electroweak epoch, around a trillionth of a second after the Big Bang, it had cooled enough for quarks, leptons, matter, and antimatter to exist, governed by gravity, the strong nuclear force, and the electroweak force. However, temperatures were still too high for the strong force to significantly influence particles, and the electroweak force had little effect on matter-energy interactions. Gravity, though present since the universe's inception, remained ineffective because particles lacked mass. It would take another energy drop and a fundamental transformation before the universe began to resemble the one we know today. Symmetry is a pervasive feature of nature, from the bilateral symmetry of humans and animals to the radial symmetry of starfish and sea urchins. Evolution favors symmetrical forms because they are simpler to construct and maintain. In physics, symmetry signifies invariance, something that remains unchanged regardless of external conditions. The laws of physics, conservation of energy, and the balance of positive and negative charges all reflect the universe's inherent symmetry. Yet, the cosmos is not perfectly symmetrical. Just as the human heart is slightly off-center, the universe has its own asymmetries. Some particles only spin in one direction. Matter outweighs antimatter, and electric and magnetic fields behave differently, despite their theoretical equivalence. These imbalances are crucial to the functioning of reality. However, in the universe's earliest moments, cosmologists believe everything was perfectly symmetrical. This balance was disrupted as temperatures dropped, leading to phase changes in energy and matter. The separation of the four fundamental forces marked the beginning of the quark epoch, where matter interactions began to shape the cosmos. The largest known object in the universe, the hypergiant star Uy Scuti, is composed of some of the smallest particles, atoms of hydrogen and helium. Once thought to be indivisible, atoms are now known to consist of protons, neutrons, and electrons, which can be further broken down into quarks. Quarks, along with electrons, are the fundamental building blocks of matter. The standard model of particle physics identifies 12 fundamental particles, 6 quarks and 6 leptons, along with their antimatter counterparts and force, carrying particles like photons, gluons, and W and Z bosons. Despite extensive experiments, no evidence suggests that quarks or leptons are made of smaller components. However, standard model is incomplete without an explanation for mass. Most of an atom's mass comes not from its protons and neutrons, but from the energy binding them together, as described by Einstein's EMC quadrant equation. Quarks, though fundamental, have their own intrinsic mass, which varies widely among particles. This disparity puzzled physicists for decades until Peter Higgs proposed a solution in the 1960s. He suggested that particles initially had no mass, but acquired it through interactions with a pervasive energy field, now known as the Higgs field. This field is mediated by the Higgs boson, a particle that completes the standard model. To explain the Higgs field to the public, physicist David Miller used the analogy of a cocktail party. A room full of people represents the Higgs field, and a popular guest moving slowly through the crowd symbolizes a particle gaining mass. Despite its imperfections, this analogy has endured. The search for the Higgs boson was a monumental task, akin to finding a needle in a haystack. It took nearly 50 years, and the construction of the Large Hadron Collider to finally detect the elusive particle in 2012. This discovery confirmed the existence of the Higgs field and provided a crucial piece of the puzzle, explaining how particles acquire mass, shaping the universe as we know it. Two of the world's most advanced particle accelerators, the Tevatron at Fermilab in the US and the Large Hadron Collider at CERN in Europe, has spent years colliding particles and analyzing debris. The challenge lay in the fact that while Peter Higgs had theorized the existence of the field and boson, his work did not specify the energy levels required to detect them or the particle's properties. It was akin to searching blindly for an unknown object in a cosmic haystack. Yet in 2012, the LHC achieved the unimaginable. Scientists confirmed the discovery of the Higgs boson, definitively proving the Higgs field's role in imparting mass to particles. This solidified the boson's place in the standard model and the field's critical influence on the early universe's evolution. A trillionth of a second after the Big Bang, the electroweak force fractured into the electromagnetic and weak nuclear forces, shattering the universe's primordial symmetry. The Higgs field emerged shortly after, endowing particles with mass. W and Z bosons gained heft, quarks and leptons acquired mass based on type, while photons and gluons remained massless. By a billionth of a second, the universe brimmed with quarks, gluons, and the raw ingredients for stars, planets, and life. The quark-gluon plasma became the cosmic forge for all future structures. Our cosmos teems with staggering diversity, fleeting massive stars, enduring red dwarfs, gas giants, barren rocks, and rare life-sustaining worlds. On Earth alone, life ranges from sulfur-breathing microbes to self-aware beings. Yet amid this variety, certain constants unchanging across time and space anchor reality. These include the speed of light 2.99792 Cheng 2 mm s, the gravitational constant 6.67384 Cheng 2 10 menons non 2m kubu k g s octrodud, and the masses of fundamental particles. Even the Higgs mechanism cannot explain why these values are fixed. The fine structure constant tilde 137th, governing electromagnetic interactions, exemplifies this mystery. Alter it slightly, and protons destabilize, matter disintegrates, or universes collapse into black holes or hydrogen haze. Such precision hints at either cosmic luck, a creator's hand, or a multiverse, where only finely tuned universes thrive. By a millionth of a second post-Big Bang, temperatures cooled to 1 trillion degrees, allowing quarks and gluons to coalesce into protons and neutrons. Despite their stability, protons harbor chaos. Their two up quarks repel, held together only by gluons' relentless mediation. Transient charm quarks even flicker in and out of existence, rendering protons a dynamic mix of real and virtual particles. As the universe aged, weak force interactions allowed protons and neutrons to swap identities until temperatures dropped further. Around 1 second old, a freeze-out locked their identities. Here, the down quark's slight mass advantage over the up quark tilted the balance, shaping the neutron-to-proton ratio, a subtle yet pivotal outcome of nature's constants. This delicate fine-tuning, set in motion within the first seconds, paves the way for a cosmos capable of complexity, longevity, and life. The why remains unanswered, but its fingerprints are etched into every atom, star, and living creature. As the universe cooled, a subtle energy gradient, favoring protons slightly lighter than neutrons, tipped the cosmic scales. This minuscule mass disparity locked in a 7-to-1 proton-to-neutron ratio, a critical imbalance shaping our reality. Protons became the bedrock of hydrogen and helium, fueling stars and enabling chemistry. Had down quarks been lighter, neutrons might have dominated, leaving a sterile cosmos of inert helium and unreactive neutron-snow stars, planets, or life. Equally pivotal was another asymmetry: matter's unexplained supremacy over antimatter. Dirac's 1928 equations first hinted at antimatter's existence, later confirmed by Anderson's positron discovery. By the 1950s, accelerators identified antiprotons and antineutrons, yet today's universe harbors barely a trace. If matter and antimatter had formed equally, mutual annihilation would have left nothing but energy. Instead, a mysterious break in symmetry spared 1 in a billion matter particles. The weak forces parity violation, exposed by Chen-Sheng Wu's experiments, offer a partial clue. Quarks and antiquarks behave asymmetrically, but not enough to explain matter's dominance. Theorists propose extinct right-handed neutrinos that decayed unevenly, favoring matter. Yet, without detecting these particles, the puzzle persists. Antimatter's destructive potential remains stark. A gram-annihilating normal matter unleashes nuclear-scale energy. While alien civilizations might weaponize it, cosmic history, shows annihilation's rarity. From supernovae to bananas, antimatter flickers transiently, dwarfed by matter's overwhelming presence. By the universe's first second, these asymmetries proton abundance, matter's edge, were etched into reality. Their origins linger in the unknown. Fine-tuning, multiverse chance, or undiscovered physics. As neutrinos from this epoch still stream through space, they may yet whisper answers if we learn to listen. The cosmos reveals intricately spiraled galaxies, vibrant nebulae, and quasars' distant beacons powered by supermassive black holes devouring matter. These quasars illuminate a phenomenon called the Lyman alpha forest, a spectral tapestry woven by ancient hydrogen clouds. As light from quasars travels billions of years through expanding space, it stretches into redshifted wavelengths. Embedded within this light are sharp absorption lines, countless dips clustered like trees in a forest, each marking a hydrogen cloud intercepting the quasar's journey. This spectral forest thickens at high redshifts, revealing an early universe teeming with hydrogen, the primordial fuel for stars and galaxies. By the universe's first second, temperatures plummeted to 10 billion degrees Celsius. The chaos of particle creation and annihilation ceased, leaving protons, neutrons, and photons as survivors. The Higgs field had already bestowed mass, while the four fundamental forces settled into their distinct roles. This epoch, once purely theoretical, now edges into observational reach thanks to projects like the IceCube Neutrino Observatory. In Antarctica, scientists drilled 2.5-kilometer deep holes using pressurized hot water, suspending 4,000 sensors in the ICEA downward-facing telescope designed to detect neutrinos. These ghostly particles, theorized in the 1930s and confirmed in 1956, stream through matter unimpeded, interacting only via gravity and the weak force. Their detection revolutionized astronomy. When a 1987 supernova's neutrinos reached Earth, they heralded multi-messenger astronomy, combining light, gravitational waves, and neutrinos to study cosmic extremes. Neutrinos also offer a portal to the universe's first second. After escaping the dense primordial plasma, they left a faint imprint cosmic neutrino background. Detecting this relic could map the infant cosmos 380,000 years earlier than photons allow. Though elusive, just 300 relic neutrinos per cubic meter exist. Their subtle influence may have seeded temperature fluctuations that shaped galaxies. Meanwhile, enigmatic giants like Dawn 618 defy expectations. This 66 billion solar mass black hole, glowing 140 trillion times brighter than the Sunday, existed just 11 billion years post-Big Bang. Such early behemoths challenge models of star-fed growth. A solution may lie in primordial black holes, theorized by Stephen Hawking. Born from density fluctuations in the universe's first second, these ancient seeds could have ballooned into supermassive monsters long before stars formed. From spectral forests to neutrino whispers and black hole paradoxes, the cosmos guards secrets etched in its earliest moments. Each discovery peels back layers of time, bridging the gap between theoretical infancy and observable reality. The challenge is that while this theory aligns with our understanding of early universe matter behavior, pinpointing when primordial black holes formed and how massive they grew within that critical 1-second window remains elusive. Mathematically, The later a primordial black hole emerged after the Big Bang, the larger its mass. Estimates vary widely from specks lighter than a paperclip's 100,000th to colossal entities 100,000 times heavier than the Sunday. How then do we detect them? In the 1970s, Stephen Hawking theorized that black holes don't just consume matter, they also shed mass via Hawking radiation. Smaller black holes lose mass faster, eventually evaporating in explosions equivalent to 1,000,000 hydrogen bombs. Any black hole below 100 billion kilograms would vanish within the universe's current age. Scientists now hunt for these explosive signatures using tools like the Fermi Gamma Ray Space Telescope. Other methods include observing microlensing effects as black holes pass in front of stars, or tracking the destruction of dense stars in their gravitational grip. So far, these efforts have only ruled out certain size ranges, narrowing the possibilities for primordial black holes. Future projects like the Laser Interferometer Space Antenna, LISA, launching next decade, aim to detect gravitational waves from these ancient relics, born barely a second after time began. On the 5th of December 2022, researchers at California's National Ignition Facility achieved a milestone. They fired 192 lasers at a gold cylinder housing a peppercorn-sized fuel pellet of deuterium and tritium. The lasers heated the cylinder to 3 million DU4 hotter than the sun's surface-generating X-rays that compressed the pellet at 400 kilometers per s. The resulting implosion fused hydrogen isotopes into helium, releasing 3.15 megajoules of energy from 2.05 megajoules input, the first net energy gain fusion reaction in 70 years of research. While modest, enough to boil 20 kettles, this breakthrough mirrors the universe's own fusion processes, mastered in stars since their birth. Humans have long been fascinated by transformation turning lead to gold or conjuring flowers from air. The early universe was a cauldron of such changes, driven by shifting fundamental forces. Even today, radioactive decay reshapes elements. Carbon-14 dates fossils, technetium-99 aids medical scans, and uranium-235 powers reactors. But fusion, which builds heavier elements, demands extreme conditions, like those in stars or the NEEF experiment. Atomic identity hinges on proton count. Hydrogen, 1 proton, has isotopes. Protium, 0 neutrons. Deuterium, 1 neutron. And tritium, 2 neutrons. Adding protons creates helium, 2 protons, with helium-4 being the most stable. Fusion requires overcoming proton repulsion via immense pressure and heat, as in stars or laser-driven capsules. Heavier elements form in supernovae or neutron star mergers. Brown dwarfs' failed stars lack the mass to fuse protium, but can burn deuterium. Yet, none of this explains how primordial deuterium and helium originated. For answers, we revisit the universe's first minute. 1 microsecond post-Big Bang, quarks coalesced into protons and neutrons as temperatures cooled to 10 million DU4C. But how did these particles assemble into nuclei? In 1948, Ralph Alpher and George Gamow proposed Big Bang nucleosynthesis (BBNA) theory, overshadowed by Gamow's whimsical addition of Hans Bethe's name uninvolved in the work to their Alpha Beta Gamma paper. BBN explains how the early universe fused hydrogen into helium via deuterium intermediaries, laying the groundwork for all future stars. Protium nuclei formed first, but neutral hydrogen atoms with electrons emerged much later as the cosmos cooled. Approximately 10 seconds after the Big Bang, deuterium nuclei, one proton, one neutron, began forming in the cooling cosmos. Yet extreme temperatures and particle energies kept these nuclei unstable. Collisions with photons shattered them instantly, creating the deuterium bottleneck that stalled nucleosynthesis. Only 300 seconds later, temperatures dropped enough for deuterium to stabilize. Under universal pressure, deuterium fused with protons, creating helium-3, then helium-4, the most stable atomic nucleus. Calculations predicted 25% helium by mass. Today's observed 23% aligns strikingly, confirming the universe's fine-tuned initial conditions. By 20 minutes post-Big Bang, cooling halted fusion. Only hydrogen, helium, lithium, and fleeting beryllium remained 12 hydrogen nuclei per helium, with photons outnumbering matter 1 billion to 1. These primordial ingredients, forged in the first moments, later fueled stars and 2022's fusion breakthroughs. Life's origins remain enigmatic. Earth's DNA, RNA, nucleobases adenine, guanine, and others might have cosmic roots. In 1969, formaldehyde in interstellar space hinted at organic chemistry beyond Earth. The 1864 Augale meteorite stunned scientists with nucleobases identical to terrestrial DNA, suggesting molecular building blocks rained from space. Over 250 organic molecules, now identified in nebulae and star systems, reveal the universe's innate chemical prowess. Post-nucleosynthesis, the universe simmered as a dense plasma for millennia. Electrons raced too fast to bond, yet chemistry simmered. Helium hydride, Hegia-1. First lab made in 1925. Eluded detection until 2019. John H. Black's 1978 theory posited its presence in planetary nebulae, where ionized helium could strip electrons from hydrogen. Cutting-edge telescopes finally spotted Hegia-1 in NGC 7027, a dying star's nebula confirming primordial chemistry's role in cosmic evolution. From deuterium bottlenecks to meteoritic nucleobases and elusive molecules, the cosmos whispers secrets of its elemental and biological potential etched in the first seconds and still unfolding. Most telescopes today are either ground-based, perched on mountains to minimize atmospheric interference, or launched into space to avoid it entirely. The Sophia Observatory, however, took a unique approach. Mounted on a modified Boeing 747, its 2.7-meter telescope peered through an open door at 43,000 feet, soaring above most atmospheric water vapor. This allowed it to detect far-infrared wavelengths typically absorbed by Earth's atmosphere. Equipped with the Great Receiver, Sophia pinpointed helium hydride ions in the planetary nebula NGC 7027, 3,000 light-years away in Cygnus. This discovery, predicted by John Black in 1978, confirmed helium hydride's presence in environments mirroring the early universe. Around 100,000 years post-Big Bang, as temperatures cooled to 4000 Kelvin, helium, the most inert element, became the first to capture electrons, forming neutral atoms. Yet, its stability was fleeting. Protons, unable to bind electrons alone, clung to helium, creating unstable helium hydride ions. These fleeting molecules marked the dawn of cosmic chemistry, paving the way for more complex structures. Today, astrochemistry explores the molecules scattered across space, from water and ammonia to exotic compounds, like dihydrogen monochloride cations. These discoveries trace back to helium hydride, the universe's first molecule, forged in its infancy. Our perception of reality is limited. Visible light is a sliver of the electromagnetic spectrum, which includes gamma rays, X-rays, ultraviolet, infrared, microwaves, and radio waves. These invisible energies permeate our lives, from the sun's radiation to Wi-Fi signals. If we could perceive them all, the night sky would blaze with color and sound, revealing the faint glow of the cosmic microwave background, the universe's first light. For its first 380,000 years, the universe was opaque, its photons trapped in a dense plasma of particles. Only when temperatures dropped to 3000 Kelvin did electrons bind to nuclei, forming neutral atoms. This recombination freed photons, allowing light to travel unimpeded and transforming the cosmos into a transparent expanse. The formation of atom hydrogen capturing one electron, helium was a monumental shift. Electrons, once free, became bound by electromagnetism, creating the building blocks of matter. This process, governed by quantum physics, required the universe to cool and expand over millennia. When it finally occurred, it marked the end of the cosmic dark ages and the beginning of the universe as we know it. From helium hydride's fleeting existence to the liberation of light, these milestones reveal the delicate balance and intricate processes that shaped our universe. This is the first light that truly illuminates the universe. What was once opaque becomes transparent. What was once plasma transforms into gas, and what was once fragmented becomes whole. For the first time in cosmic history, we can finally glimpse the universe's earliest moments. Scientific breakthroughs are rarely accidental, and even fewer lead to Nobel Prizes. Progress usually demands years of dedication, incremental research, and investment. Yet, in 1978, the Nobel Committee defied convention by awarding the physics prize to two men whose groundbreaking discovery was, in many ways, a stroke of luck. In the early 1960s, Bell Labs built a 20-foot horn-shaped antenna in Holmdel, New Jersey. Originally designed for satellite communication, the antenna became obsolete within years. Rather than discard it, Bell Labs offered it to researchers Arno Penzias and Robert Wilson, who aimed to study radio signals from intergalactic space. However, their observations were plagued by a persistent, low-level hiss. Their researchers ruled out interference from New York City, military installations, and even the Milky Way itself. The noise seemed to emanate uniformly from the entire sky. Convinced it was an instrument error, they inspected the antenna and uncovered it was infested with pigeons. They speculated that the bird's droppings, described as a white dielectric material, might be generating heat and causing the noise. After multiple attempts to remove the pigeons, including some drastic measures, the hiss remained. With all potential sources of error eliminated, Penzias and Wilson began to consider that the noise might be cosmic in origin. They consulted Robert Dicke, a Princeton astronomer, who had been developing a theory about the early universe. Dicke proposed that the Big Bang left behind a faint glow, stretched by cosmic expansion into microwave wavelengths. This cosmic microwave background, CMB, would be the oldest light in the universe, dating back to 380,000 years after the Big Bang. Penzias and Wilson had inadvertently discovered the CMB, earning them the 1978 Nobel Prize. While Dicke's cyclical universe model was later disproven, the CMB's detection confirmed the Big Bang theory. The faint glow, now cooled to just 2.7 degrees above absolute zero, is the earliest observational evidence of a hot, dense, and expanding universe. Later studies revealed subtle variations in the CMB tiny temperature fluctuations of a few hundred thousandths of a degree. These variations, mapped by projects like the Cosmic Background Explorer, COBE, the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck Telescope, provided a blueprint for the universe's large-scale structure. Denser regions attracted more matter, eventually forming stars, galaxies, and clusters. These fluctuations originated from quantum effects in the universe's first moments, amplified by rapid inflation. But the CMB also holds another clue: the imprint of sound waves that rippled through the early universe. Before atoms formed, the universe was a dense plasma where sound could travel. Gravity pulled matter inward, while photons pushed outward, creating concentric ripples known as baryon acoustic oscillations, BAOs. When atoms formed 380,000 years after the Big Bang, these ripples froze in place, leaving behind a pattern still visible in today's galaxy clusters. Modern BAOs span about 500 million light-years, serving as a standard ruler for measuring cosmic expansion. The CMB, though faint, remains a treasure trove of information. It reveals not only the universe's origins, but also its future. Trillions of years from now, this ancient light will fade, but for now, it offers cosmologists a window into the cosmos' earliest moments. For billions of years, within the swirling spiral arms of the Milky Way, massive stars ignite, burn intensely, and die dramatically, expelling their spent fusion fuel back into the galactic cloud for recycling. This gas, enriched with heavier elements forged during stellar nuclear fusion, becomes the foundation for a new generation of star sand, for the first time, planetary systems. On a fragmented spiral arm, about 25,000 light-years from the galactic center, a star flickers to life around 4.6 billion years ago. Mirroring the galaxy on a smaller scale, dust and gas swirl around it in a flattened disk. Dust clumps into pebbles, pebbles into boulders, and eventually boulders into rocky worlds. These worlds compete for stable orbits around the yellow star, enduring catastrophic collisions before settling into positions they will occupy for the next 4.5 billion years. On the third rocky planet from the Sunday, as the heat from its violent formation dissipates, water condenses into oceans, atmospheres form, and plate tectonics begins recycling rock at the surface. Somewhere in these oceans, life sparks into existence, adapts, evolves, and fills this unique world with a new kind of creation. Chemistry transitions to biology as countless life forms thrive in the seas, on land, and in the skies. Then, seemingly out of nowhere, a sentient mind emerges to ponder its place in the universe. Despite understanding the broad sequence of events that led to the Milky Way, the Sunday, Earth, life, and humanity, gaps remain in our cosmological knowledge. How did the uneven mix of atoms formed shortly after the Big Bang lead to all of this billions of years later? Was this outcome inevitable, or could the universe have taken a different path? Simulating the matter and energy present during atomic recombination and the cosmic microwave background's formation reveals a universe subtly but significantly different from our Sun, with fewer galaxies, slower star formation, and delayed planetary systems. In these simulations, life might lag or even be absent. Clearly, a missing piece of the puzzle exists, one that ties everything together. This missing piece, however, remains invisible to cosmologists. Around 380,000 years after the Big Bang, light escapes its matter prison, allowing photons to travel freely through the expanding cosmos, though they lose energy as space grows. The universe is no longer opaque but remains dark. The intense energy of formation fades, and millions of years pass before nuclear fusion reignites, concentrating energy once more. This period, known as the Cosmic Dark Ages, may seem uneventful, but it is during this time that dark matter begins shaping the universe's future. The concept of dark matter emerged in 1933 when Swiss astronomer Fritz Zwicky observed the Coma cluster of galaxies located 320 million light-years from Earth. The galaxies moved too quickly for the cluster to hold together based on visible mass alone. Zwicky proposed the existence of unseen mass, which he called Dunkelmaterie, dark matter. Decades later, astronomer Vera Rubin studied the Andromeda Galaxy and found that stars at its outer edges moved as fast as those near the center, defying expectations. She concluded that visible matter accounted for only 15% of the galaxy's mass, with the rest being dark matter. Today, astronomers believe dark matter plays a crucial role in shaping the universe, outweighing normal matter 6-1. Yet, its nature remains a mystery. One theory suggests dark matter consists of ordinary baryonic objects like black holes, neutron stars, or brown dwarfs, collectively called MACOs, massive compact halo objects. However, as technology advances, the likelihood of such objects remaining undetected diminishes. Another, more favored theory posits that dark matter is composed of weakly interacting massive particles, WIMPs, a new type of particle outside the standard model. Despite decades of research, Wisconsin MPs have yet to be detected, leaving dark matter as one of cosmology's greatest enigmas. Dark matter would not interact with normal matter through any known fundamental forces except gravity, yet it would possess enough mass, or exist in sufficient quantities to account for the universe's missing 85% mass. The search for these elusive particles, whether in particle accelerators or across the cosmos, continues, but with limited clues. The journey may be long. Whether dark matter consists of MACOs, Wisconsin MPs, or something entirely different, it has likely existed since the universe's earliest moments, hidden alongside tangible matter. During the cosmic dark ages, around 1 million years after the Big Bang, dark matter began shaping the universe's large-scale structure. The cosmic microwave background reveals that matter and energy were unevenly distributed at the time of atomic recombination, and dark matter likely followed this pattern. In those dark millennia, dark matter's gravitational pull caused it to clump together more rapidly and densely than normal matter. These dark matter structures acted as templates, drawing baryonic matter into invisible gravitational wells and forming vast cosmic filaments, nodes, and gas clusters that became the birthplaces of the first stars and galaxies. From this point onward, the universe's evolution became inevitable. The first 1,000,000 years of cosmic history set the stage for the next several billion years of astrophysical creation. The universe cooled, allowing comprehensible physics to take hold. The four fundamental forces became distinct, governing all interactions, while the nature and quantities of matter stabilized, providing the ingredients for stars, galaxies, chemistry, and ultimately, life. For 8 billion years, the universe evolved as expected. However, between 5 and 6 billion years ago, shortly before the formation of our solar system, something changed. The first indication of this shift was observed in 1998, when astronomers studying distant supernovae, often referred to as standard candles due to their predictable brightness, discovered that these celestial objects exhibited greater redshift than expected. This unexpected finding suggested that the universe's expansion was not slowing down, as previously thought, but was instead accelerating. This groundbreaking discovery was later corroborated by additional evidence, including measurements of baryonic acoustic oscillations and the distribution of galaxy clusters, which collectively pointed to the existence of a mysterious force driving this accelerated expansion. This force was dubbed dark energy, and it has since become one of the most profound puzzles in modern cosmology. Since that pivotal discovery, our solar system, along with the rest of the universe, has existed in an era dominated by dark energy. Despite its significant influence on the cosmos, dark energy remains as enigmatic as dark matter, another major component of the universe that defies easy explanation. One of the leading theories to explain dark energy revives an idea originally proposed by Albert Einstein, the cosmological constant. Initially introduced by Einstein to represent the intrinsic energy of empty space, the cosmological constant has been reinterpreted as a potential explanation for dark energy. However, this theory raises more questions than it answers, as the origin and nature of this energy remain unclear. Another possibility arises from quantum theory, which suggests that dark energy could be linked to vacuum energy, a form of energy that emerges from the constant creation and annihilation of virtual particles due to quantum fluctuations. While this idea is theoretically appealing, calculations of vacuum energy on cosmic scales produce values that vastly exceed the observed rate of the universe's expansion. This discrepancy has led some cosmologists to propose alternative explanations, such as quintessential dynamic energy field that can vary in strength and even change from attractive to repulsive over time. Despite these intriguing ideas, the lack of experimental evidence or direct observations means that the true nature of dark energy remains one of the greatest unsolved mysteries in science. Today, the composition of the universe is estimated to be approximately 68% dark energy, 27% dark matter, and less than 5% normal matter. Familiar atoms and particles that make up stars, planets, and everything we can see. From these fundamental ingredients, the universe has evolved over an astonishing 13.8 billion years, shaped by the physical laws and constants established in the first moments after the Big Bang. In fact, the rules governing the cosmos were largely set within the first 10 trillions of a second, a timescale so brief it is almost beyond human comprehension. As we continue to explore the history of the universe, each discovery brings us closer to understanding the forces that have shaped our cosmic whole. From the earliest moments of the Big Bang to the present day, the story of the universe is one of constant change and evolution. Thank you for joining us on this journey through space and time with Space Shock. We invite you to share your thoughts as we venture further into the mysteries of the cosmos, beyond the first million years of cosmic history. Stay curious, and we'll see you next time.